Hello. So this is part I, where we're going to talk about potential energy graphs. Now, normally we say PE for potential energy, but you'll also see a capital U to represent potential energy. So that's a really common way that you'll see potential energy. And normally it is a function of x. Okay? And so a lot of times you'll see a graph of something like Ux, okay? And then there will be some sort of graph here. So maybe it will look like this. Okay? And so they give you this graph of my potential energy and direction. Okay? And the problem will frequently say something like it starts at x equals 0, and maybe it has 10 joules of Ke. Okay? And so let's go ahead and put like 10 here. Okay? And so at first this looks very daunting, but there's actually a very easy way to visualize this. Okay? So all you need to do is put a marble on the place. Okay? So wherever they're having you start, go ahead and just imagine putting a marble at that spot. Okay? And then imagine if it's moving that you like flicked it. Okay? Now, up to here, this is where my 10 joule mark is, right? And if all of this kinetic energy is converted into potential energy, okay, the highest it can possibly go is up to there. Okay? So you can get all the way up here, right? But then it runs out of energy. So now what's going to happen? Well, it's just going to come back down. Right now it's going to go up this hill, come down here, and then get here, right? And then what's going to happen? Well, then it's going to come back down, and we end up with this long cycle. Okay? Frequently with your potential energy graphs or even a function, you end up with some kind of oscillation, right? Where it's going back and forth, right? Or it's kind of even taking this more interesting path up and down. Okay? But the way that you visualize this is just imagining that you put a marble here. I'm just going to put a marble here, and then you can actually find out what is happening, right? What path is this marble going to travel on? Okay? It's really important to find out your total energy that you have, or the total mechanical energy, so you know that this is where the maximum that marble can end up. Okay? It's possible that, let's say, it doesn't oscillate. So it maybe does something like this, and then it gets flat, right? It has this asymptote here. Well, if this is my maximum total energy, right, then it's going to come up here, and it's just going to keep going forever. Okay? Now, let's just kind of review a little bit. So we know that work, which is equal to the change in energy, is equal to the integral of F dx, right? Or you can put F dot dr, right? Those are kind of the same things. Okay? Which means the relationship between potential energy, U, and F is this, right? So I need to take the integral to get my potential energy. But sometimes they'll give you the potential energy and they'll want you to find the force. Okay? So if you need to take an integral of force to get the energy, what do you need to take of energy to get the force? Hopefully you figured it out that it is the derivative. Okay? So if we take the derivative of the force, the derivative of the energy, we actually get the force. Okay? Now there's one caveat to this. When the potential energy increases, the force is actually in the opposite direction. What do I mean by that? Well, if I have this marker, okay, if I want to increase its potential energy, which direction does it need to go? Gravitational potential. It needs to go up, right? I need to push it up. Okay? But the direction of the force is which way? Down, right? So our formula is actually this. Negative du dx equals F. Okay? And it's really important that when you look at your graph, to realize that the derivative of u du dx, right, that derivative is my slope. Okay, so you can also actually see your slope at different points, right? And that will tell you something about the force. For example, the force at this bottom point here, at the bottom of that parabola, is what? 0, right? I know it's 0 because the slope is 0, okay? And so you can also find equilibrium points, okay? So this would be an equilibrium point because the force is 0. This is an equilibrium point because the force is 0. And this is an equilibrium point because the force is 0, okay? At those points, I could end up, okay? You can only end up at an equilibrium point on a potential energy curve because any other spot, there's a force pushing you, and you can't stand still when you have this force, this unbalanced force pushing you, okay? So this is actually an important formula to know. It's kind of easy to remember, but this one doesn't have that negative sign here. This one does. The negative sign is actually coming from that dot product, so that's the reason we have that negative sign there, okay? But this one is not actually on your formula sheet, so it is important to remember. Now, you have this to kind of help you remember, but you don't explicitly have that, okay? Remember, if you have any questions or concerns, or you didn't really understand something, send me an email and I'd be happy to clarify for you, okay? So this is the way that you visualize your potential energy curves.